Hello, everyone, and a very good morning to all of you. Distinguished delegates and participants from SAARC member states, ladies and gentlemen, I am very thankful to all of you for joining us in this SAARC webinar. My name is SN Javed, and I am a research fellow renewable energy working at SAARC Energy Center. I shall be moderating today's webinar, the aim of which is to introduce the system design and simulation software and to enhance the capacity of the SAARC professionals on using this software. First of all, allow me to briefly speak about the important role played by our Center SAARC Energy Center in the South Asian region. The center, being a regional institute and a technical arm for the SAARC organization on energy matters, has contributed tremendously through capacity building and regional cooperation of the member states. This center started its operation in the year 2008, and in the last 10 years, the center has emerged as a vibrant and effective SAARC institute which has played its role in all regional level energy initiatives. The center has to now carried out 100 plus interventions. The reports of all these interventions are available on SEC's website, free of cost to anyone interested. Ladies and gentlemen, globally there are many professional softwares for designing solar PV systems that allow the users to accurately analyze different configurations and to evaluate the results and identify the best possible solution. There are many software in the market which are extensively used by industry and researchers for designing simulation of solar PV systems. These software include extensive meteorological data for different cities and PV systems components databases, as well as general solar energy tools. These softwares are geared to meet the needs of architects, engineers, researchers, and are helpful for educational training. Ladies and gentlemen, we have already conducted one of the same webinar on 23rd April, and this is the second series of the second webinar in continuation of the first one. So in this webinar, among the many available software, Homer is one of the best and famous software used around the globe for solar PV system. The Homer team, we are very thankful to the head Peter and for Andy for agreeing to contribute with us in this webinar. Andy Cruz, who's the Vice President of Business Development in Homer Energy, I would like to introduce him. For nearly 30 years, Andy Cruz has been involved in international marketing, sales, development of certification, standards, and public policy. Andy was a co-founder of Southwest Wind Power, a startup small wind company that grew to be an internationally recognized brand within the clean energy industry. Southwest Wind Power sold more than 180,000 wind generators worldwide. Later, he joined Endurance Wind Power and established one of the first small wind leasing programs in the US. Just before joining Homer Energy, he worked as a consultant to a number of wind and solar companies in Europe, and he was awarded Exporter of the Year by the US Export Import Bank, and he received the President Award from the US Department of Commerce. The American Wind Energy Association awarded him Small Wind Person of the Year in 2009. So, ladies and gentlemen, you will have the opportunity to ask questions from Andy by typing your questions or clicking to the raised hand option into the attendees pane of the main window of GoToWebinar software. You may send in your questions at any time during the presentation. We will collect them and address them during the question answer session at the end of his presentation. So I am now giving the mic to Andy. So Andy, over to you for your presentation.
Electronically. Let me turn my screen on here. There we go. Can everybody see my screen okay?
Yes, perfect, Andy. It's visible.
Okay, very good. Again, thank you very much for this opportunity to speak to everybody there in Pakistan. Again, yes, my name is Andy Cruz, and I'm Vice President of Business Development. My presentation today really is going to cover a little bit about what's going on in the marketplace globally. In terms of energy generation from a distributed energy perspective, and also then getting into a little bit about our software and how it's helping develop that market. So what we're seeing in the marketplace is some very interesting trends. We're seeing where distributed energy and the microgrid space is continuously changing. You know what? I have to do something. I very much apologize for this. I was looking at that, and this is a slightly different presentation. That's almost starts the same here. So one moment, please. Okay, let me get this right. I really apologize for that. Uh, okay, one more time here. Okay, so what we're seeing in the world today, as was mentioned, I've been in this industry for about 30 years, and when I was first starting out in the industry, much of our electric grid received its energy from centralized power stations, and it's still quite popular that way around the world. But what we're seeing now is an evolutionary change, going from more centralized power stations to decentralized stations, where electricity is generated not just in big power plants, but also on tops of factory roofs and homes and office places around the world. And so it's really facilitating. There's a big question, of course, which we'll get into in a moment, is exactly why that's happening. But just to start off with just a little bit about what exactly is a microgrid and what is distributed energy. A microgrid is a system that produces energy autonomously for a given load in a specific area. And it can be comprised of solar systems, wind turbines, generators, control systems, energy storage, and also diesel gensets. And these systems can either be connected to a larger grid or it could be run autonomously by themselves. And there's a lot of reasons why people are exploring this new industry. Some of it's because of a weak grid. You have a lot of power outages and you want to sustain energy for a particular application. Economics, which we'll talk about that in a moment. Perhaps clean energy mandates that are stated by the government. To help support the grid is another reason. And then also addressing things like peak demand. So in the summertime, when there's a lot of load on the grid because of air conditioning, people are deploying these microgrid systems to help reduce those demands. So a lot of applications where you'll see microgrids so in there, as I mentioned, there's kind of two different markets within microgrids. There are telecom sites, remote homes, forward operating bases in military applications, villages and small communities, island nations, and mining operations are typically what we see in the off-grid microgrids. And in the past, before the evolution of more the modern day microgrid, a lot of what you saw is just a single generator or something like that was producing the power. Now what we're seeing, and it's more complex, but they're more cost effective and they're more reliable, is the use of these multiple technologies for that same application. And then of course, then there's on-grid microgrids, which are systems and it's designed in a very similar way, but they all have a connection to the main grid. And common applications for those are in hospitals, campuses, data centers, communities, factories and offices, hotels, and other applications like that, where again, where you get perhaps your primary power from the electric grid, but these systems will either supplement that system and also be there available when if and when the main grid goes down. So the big reason why this is all happening is more so because of the cost of renewables and the cost of energy storage. And since I was in this business in the late 80s, and the cost of one solar panel would run you about $12 US dollars per watt. And today the prices are around 60 cents a watt. So we've seen a significant decrease in the cost of solar. And likewise with wind, the first wind turbines would produce energy for 75, 80 cents a kilowatt hour. And nowadays they're as low as 3 to 4 cents a kilowatt hour. And so now what we're seeing is a new evolution, and that's in energy storage, largely driven by lithium batteries, which I'll talk a little bit about that in just a moment as well. And then other technologies like flow batteries and whatnot. In all these cases, we're seeing a significant decrease in the cost of these technologies as well. So looking at these technologies combined together with software and inverter technologies is really driving the desire to create these more distributed energy systems, because they can produce energy for the same price as what the grid charges, and in some cases even less than that. And so when we look into the future of this emerging market, of these emerging microgrids, all the experts are saying that this is expected to be a $35–40 billion industry within just the next few years. And we're pretty much on track. If anything, we're probably a little bit ahead of what a lot of what the experts say, largely because the cost of energy storage is falling faster than what we had predicted. And so what is occurring then through this whole process is a great deal, as I said earlier, a great deal of interest in microgrids around the world. This map that you see on the screen, each dot represents a microgrid model that has been run using our software around the world, and since just 2014. And so really, I guess you could say January 2015. And this just demonstrates the level of interest by people around the world in using microgrids. I also have even in Pakistan, there's been over 650 microgrids modeled in your country there. And so because of all this interest, because of the demand, the cost of these technologies and how they're decreasing, we're seeing then major companies of every size, and also development agencies like the IFC or the World Bank, they're all recognizing this is truly what the future is going to be. It's also partly driven by CO2 emissions and environmental issues as well, trying to reduce diesel fuel CO2 emissions from diesel fuel generators. But in the bigger picture, it's really just about the economics, which is really driving this. So these reasons together are really helping build that marketplace. But the big question comes about is when you look at a microgrid in today, there are a lot of different choices that are also evolving. As I mentioned, solar and wind and storage. But on top of that, there's already the already existing or already mature technology generators. But then there's also combined heat and power systems, small types of hydrokinetic, run-of-the-river kinetic systems, fuel cells, and even other emerging technologies are all coming into place. But when you have these choices, the question is which one or which group of them makes the most sense to deliver the energy in a particular location at the lowest cost of energy. And that's the biggest challenge. When you have a place, say, it's in northern Pakistan, and you've got a village there, and you're trying to figure out, well, I've got these choices. How do I know how much of what technology is going to give me the lowest cost of energy? And that's where our company Homer comes in, is it helps answer that by looking at the environment at that location and delivering the right combination of technologies. So the variables, of course, it depends on the available resource. Well, how much solar is in that location? What's the wind there? What's the temper variations there, because they have an impact on the performance of a battery? And then what kind of loads are there? How large is that load, and how much energy is being consumed, and when does it occur? Because they don't necessarily match up with the load with the available solar resource or the wind resource, for example. But then there's also what kind of maintenance has to take place in the equipment. Is there a grid, or is there not a grid, or is it a weak grid and it sometimes works and sometimes doesn't? And then there's other on-the-ground conditions that also have an impact. And so the software is there to help try to answer those questions about what makes the most sense. So Homer, what it stands for is a hybrid optimization of multiple energy resources. And what that is saying is that what we look at for is not just one technology, perhaps a solar panel on a roof and it works when the sun shines. It's when you start combining these technologies together, so hybrid, and it's trying to figure out what's the optimal mix of those technologies that makes the most sense in that location. It's a technology agnostic platform. It works with virtually any kind of distributed energy technology and helps you try to, again, answer those questions. Specifically, Homer Pro, it provides a very unbiased result for the questions that you're asking about that particular project. It simplifies the complex process of determining what's the lowest cost of energy. And and as I said, also it can model virtually any combination of these technologies. So just briefly how Homer works, and then we'll go into a model a little bit later and demonstrate the actual functionality of the software. You begin with a series of inputs in the software. You need the load profile. Again, how much energy is being consumed and when is it being consumed? Or you can even simulate that as well. If you don't know what the exact number is, you can actually create that one yourself, and we have tools to help you do that. And then let's look at the site-specific resources. We have a database that covers the entire planet of what the solar resource is over the last 22 years, and what the wind resource is, and what the temperature is. So when you pick a location with our software, you'll see in a moment, we can tell you exactly what they are. So that location, where it is, it's in Baluchistan or another region that that has no reference other than just a GPS point. We can tell you what those resources are at that location. And then it's deciding which components make sense and which ones do not. Perhaps wind will work, perhaps it won't because there's not a wind resource. So it's selecting those right components to do that. And once you've actually put all the pieces together about what you think the project should look like and what the load is, then you run the analysis. And it happens in 3 different levels. The first one is just a simulation of the project. And then it goes through each time step and then looks at each simulation. And then the model will then optimize those simulations to come up with the right solution. And then on top of that, we have a third layer, which is a sensitivity analysis, which helps you analyze what we call what-if scenarios. What if diesel fuel prices go up by 20% next year? What if interest rates fall by 5% next year or 2 years from now? Homer helps analyze that and tells you what the impact potentially could be on your project if those things happened. So after you finished running the results, running the analysis, you end up with a set of results, which is what we call the combination of economics and engineering. First and foremost, the software is there to try to help understand that question about what's the least cost solution to your project. What can deliver you the lowest cost of energy for that particular location? And as you can tell from every environment is different, every project's going to be a little bit different. And we try to take the complexity out of that. So we give you system sizing, we'll give you performance characteristics, we'll give you financials and all kinds of other reports that can help you make that decision as to, does this project make sense to do or not? So Homer also, as a company, in addition to its software, also provides a lot of consulting services around the world. We work with a lot of governments and organizations to help deliver them information specific about the microgrid and the emerging DER market. And we also then provide training services as well. So as a company, we're still a very small business, but we have a large footprint around the world in helping deliver the solutions that people are looking for and understanding the economics of a project. So I will leave this slide deck for later, and if anybody would like to learn more about the company and the software, they can certainly contact me or go to our website as well. So with that, should we ask for any questions, or should we just go right into the software?
Andy, I think you can go on with the full presentation along with the case models, and then we will address all the questions at the end of your presentation.
Okay, very good. So this here, what you see in front of you now is the platform of the Homer Pro software. This is what we call the main landing page. It's really a very simple but elegant software. You begin with the top here. We have a ribbon which has all the primary control systems. Here in the window here is where you can select any kind of location. Not sure if I spelled that right. There we go. So it will pick any location, and you can pick any spot. For example, right here, we could just drop a pin there and select a project. And there's a lot of different ways that you can view this as well. You can change the viewpoints to make it more accurate, but you put in an address or a GPS point here, and you select the location. You name the project. Get this right. And then you can make comments about the project here. And these are important to after you've run the report, you can make comments, and then as you generate the reports, you can then use that in your project. Down here, we have a lot of the primary areas about finance. We have discount rates, inflation, annual capacity shortage. This relates to just looking at more performance. If there's times that you can afford to have no energy because the peak is too high and it's too expensive, you can put what we call capacity shortages in there. And then project lifetime, which reflects, of course, trying to understand the economics of that, of all the components within that design. So you set those in the very beginning, and you just begin with going through each step of the process I just mentioned earlier. You begin then, first of all, with developing a load, and we have a lot of different ways that a load can be created. But for this, in this case, what we're going to do is sort of like a community load. With a peak month also in July, and it's going to quickly generate a synthesized load. And within this, you can make any kind of changes that you want. So if you have a community or a building or a factory or anything like that, it's all done exactly the same way. And from in here, you can make your adjustments to what that load might look like. And in some areas, I know some like communities, they have a festival in the middle of the week, or sometimes at the very end of the week, and you can make adjustments according to that. And so the next step, once you've developed and understand your load, then you start working on the components. And as I mentioned, we can model virtually any kind of component that is used in the distributed energy application. We'll start off with a generator, and the generators can be done in a lot of different ways. And for the sake of this presentation, we would use just an auto size generator, which means that Homer will decide what size generator you'll need based on that particular, on that particular load profile. And then, but at the same time, we also have, I'll show that in the next slide here. So you select that, and within the generator, there's a lot of different variations within it as well. If you're looking for like a type of fuel, and it's not diesel, well, we can select that, and so Homer would then reflect whatever type of fuel that you want the system to use. And same way with photovoltaics. We'll start off with generic flat plate, and this is a little bit interesting in this particular one, and I'll explain this in just a minute. But what we have inside of this is also a very large catalog, Homer then looks at all the specifications of each of the generators or storage batteries or wind turbines and solar panels, and we build in all the specifications that help it properly model that particular component. So it makes it very convenient. You can also, if we don't have one, if you have a particular type of generator that we don't have in here, there's also a very easy way of building your own components as well. And so we'll just add some photovoltaics into this. Oh, I wanted to. So let's see here. Go back to here. So one thing I want to point out too is you had a class earlier, and you were a couple days ago, and you were helping to use a design tool called PVSys. Well, this is what we call the PVSys wizard here. And so if you have a particular building or a location where you have a limited amount of PV, Homer doesn't know that. When it calculates runs the calculation, it's going to assume that you have as much room as you need for your photovoltaic array, but you might be constrained to a certain location. Well, you build that in PVSys, and you can easily use the wizard and pull that data right into Homer through that, thus limiting the size of the PV array that the microgrid can operate on. So it's a very handy little feature that we just recently came out with. And so same with wind turbines. So this is, you can select any kind of wind turbine in here. We have a complete catalog from less than a kilowatt to 1.5 megawatt wind turbines, or 4 megawatt machines from Enercon, for example. Actually, it's a 7.5 megawatt. And so we won't add a wind turbine into this at this moment. And then we have, again, storage, and we're going to add some storage into this as well. And in each step of it, you'll see that there's costs associated. In some cases, we put in the generic components, we put in the cost. Usually the other components, there's no price in there. That usually you have to obtain that from the manufacturer or from a dealer in that area. And so here in this particular application, we're using a lead acid battery, but you can use just about any kind of battery that is manufactured today, and Homer knows how to model that. And then finally, in the inverters, you need to add a system converter as well. So once you've got all the components built into it, one other thing I have to add to it is resources. Oh, by the way, before I leave components, let me just go through some of these other areas. So within each of these components, you also have if there's a design of a generator that just does not exist, it's not a regular generator. Maybe it's you're using a wave, tidal wave machine or something like to produce electricity, or something very unique. You can use the custom control or custom component to actually design that. And we also then in schools and universities where they have combined heat and power systems, we have the components here and here to do that. And then we have a couple different types of hydrokinetic, and then standard hydro systems. So this is more of a run of the river type hydro system, and this was more with dams. And finally, we also have a fuel cell component as well, so where you need the reformer and the electrolyzer and the hydrogen tank. So this is what makes up all the different components that will you can choose from to design that system. And finally, now is the resources itself. So we want to start off with putting the solar information in. And again, like I said, we've got this global database. So if we want to know what the resource is for the HORA, we just click on that. And so this basically demonstrates this is the solar radiation data for over the last 22 years in Pakistan there. And then the same with wind, we can look at that and do the same thing. Not a very good wind site, as I kind of thought it would not be. So it runs somewhere about 4.5 to maybe 5.5 meters per second. It's the windiest time is in June in that region. And finally is temperature. We need that to understand for battery variations and solar performance, solar panels performances. So it gets quite warm. It looks like in the summertime. In June, it gets to about 32 degrees C there. So these are all the different metrics that you need. So before I'm not gonna run this model because it'll take too long. So I'm gonna show an example of what it looks like, the output of a pre-made one. But I do want to show you just some of the other features that are also available in the tool. Again, you saw some of this already in the initial landing page, but we also have some other variations in the economics. So it's looking at perhaps if you are designing the system and you want to plug in a number for your basically your fixed capital costs that are not associated with the components, you would put that here. Maybe roads or roads and power line infrastructure and whatnot would go in there. You would make adjustments to your lifetime here. So if it's a 20-year project or a 15-year project, that has a direct impact, of course, on the economics of the project. And the other ones we've already discussed. We can also build in certain types of constraints within the design as well to help limit the model in certain ways. If emissions is an issue, you're trying to reach a specific goal with the project in terms of CO2 emissions, we can make adjustments for that. And I want to get to multi-year. And this one here is another relatively new feature as well. So Homer traditionally does what we call an 8760 or a 1 year analysis of the project. We can actually go out though after 10, 15, 20, even 40 years if you want. And what we're doing is we're taking into account the degradation of all the components within that design, when they need to be rebuilt, how many hours before rebuild. So we take into account all of those costs associated with that. So you're not looking at just how does this look after the first year, but how does this look after year 22 or year 25? So it's a very valuable tool to help look at the long-term analysis of the project. So this is, again, it's a very, very handy tool and a very easy tool to really, to get to understand and how to use. So I want to go now to this one here. So it'll take a moment for this to open up. But also what we've done is we've put together a bunch of samples in the back of the software, so it makes it very easy for you can take a look at one that's already built, how it works, and kind of build that in your mind about what are the different things that you need to do to make it operate correctly. And here we go. Okay, so this is an example of a Philippine village. It consists of 2 wind generators, a PV array, energy storage using looks like lithium, I guess a lithium battery, inverter. This is your load, and this is your generator. So this is a hybrid system using 3 forms of energy generation and one storage. We've plugged in some basic information about the project itself right here. And then we've got down here basically we've left this pretty much the same. So if we want to look at the electric load, we can look at that right away. So this is what the sample village looks like. It has about a 2 kilowatt average daily load. I guess so. And let's see here. And the components, we can look at a lot of the different generators in this system here. So this is basically the capital costs, what we've put into it, what the O&M costs are, what the replacement cost is after it's lived its life. It has a 15,000 hour life on it. And this is kind of one thing that's kind of handy. If the generator already exists there, you can actually change the life of the generator, plug that generator into your model, put in the remaining hours and minimum runtime, and basically shorten that life of the generator if it's already installed, and then put in the replacement prices so that you can actually continue to use the existing equipment until its life is over with. And so the wind turbines, they were using a generic 3 kilowatt and a generic 10 kilowatt, probably a Berge wind turbine or something like that. And then energy storage, let's use a lead acid battery here, at a capital cost of about $300. So I'm going to go to the results panel and show you kind of what it looks like after the model has been run. Now this one here has run a number of sensitivities, so that you'll see it's a little bit of a busy screen. The top screen here is the sensitivity cases, which just gives you a lot of different variables that you might have considered in. Down here is the optimization results, and these are the most important ones. When this was run, you can click on the overall. If you're just curious about how many different simulations did it run, it ran literally thousands of simulations to get to the answer that we were looking for. And the winner of this thing was not wind at all. It was solar and diesel and storage. And so I'm just going to double click on that item. Well, before I actually go there, you can get a quick overview of what's going on here. The net presence costs, that's what we're using as the as kind of the main objective, is which has got the lowest net present cost. It gives you a cost of energy, which also results in the lowest cost of energy. We also can look at the operating cost per year, initial capital costs of this whole project, and the renewables contribution and fuel consumption. So it goes all across there. It just gives you can even customize this bar to display whatever you would prefer to see. But to get the answers, you just want, oh, I don't like that. Oh, I'm having a problem with my hard drive. This is not good. Let's see here, what I can do here. This is quite embarrassing. I've had some problems with my hard drive lately, and I'm not going to be able to show. This is really not good. Okay, well, I'm hoping I can see something, but I'm not sure if my computer's going to allow me to do that right now. It's doing some really strange things at the moment. Bear with me one moment. Let me see if I can get this thing to. No, it's not going to. It's not going to allow me to do this. Oh, goodness sakes. I sincerely apologize. I'm not going to be able to show the what the model output looks like, because I've been running into some problems with my hard drive is having some problems here. So maybe I can turn off a few things here, and that might help a little bit. Let's see here. Without losing you. So okay, let's see if it just gives me just enough. Good. I'm so gluttonous. Okay, so when you double click on this item here, it's going to give you the answers to the end results, and it's going to give you a very detailed analysis of exactly what the project looks like. You can begin with the cost summary, and you can look at this in a couple different ways. So you can look at the cost of each of the components within the design. The diesel genset costing the most, of course, which includes the fuel costs as well. And you can look at this in a couple different ways as well. Let's see here. By cost type or by component. So we're looking at capital costs, operating costs, or you can look at each individual component. Up above here, and you can look across. We have a couple of different ways to look at this. This is the cash flow, or you can either look at it as a table or as a bar chart. And this is looking at year by year how much money is being invested. So the year one, of course, has the greatest investment, and then these are the operating costs throughout the each year after that. If you want to look at comparing the economics, so when we compare economics in a situation like this, an off-grid system, what we're comparing to is just a diesel genset only. So if you did nothing else out there but put a diesel generator, it has a significantly higher operating cost. And if you use the recommended design, this system would pay for itself in about 5.7 years. So it's a pretty reasonable payback period to invest in the solar and storage as compared to just the diesel only. And then the electrical, all through here is just a variety of just really great charts that kind of give you a perspective of what's going on in the design, what the diesel contribution is and what the solar contribution is. And here's a little overview of fuel costs. The diesel fuel, this is the diesel generator operating. This here is what we call kind of a heat map of the system. So this gives you a 24-hour day, 365-day view of what's going on with that generator. When it's off is in the black, and when it's on, you know, of course, it really gets into just a little bit here and there. There's a couple moments where it's peaking out at its rated capacity, but for the most part, it's running in the 2.4 to 3 kilowatt range. Renewable penetration is another example of just looking at the renewables throughout the day. And then also the battery, how hard it's being charged. And when I look at this, it's being used very heavy, or it's the orange means it's 100% charged. And you can see basically during the early morning hours and the evenings is where it's discharged the most. So another way to look at it is also with what we call the time series plot. And this here just compares different components. So we have an AC primary load, and maybe we've got diesel output here. And it doesn't look very nice right now. But if we break it down here, we can look at exactly what's going on through this design. So we have an AC primary load, a DC power, and then maybe we got some PV output power on top of that. So this really shows you day to day or hour by hour what exactly is going on in the design, in the simulation. So it's a very handy tool to try and do an analysis on, you know, if you're having too much renewable penetration, how is that happening? Sometimes that's not a good thing because you can get voltage spikes if you've got too much energy that's on the system that it cannot handle. So, and finally, just one other thing I want to show you too is a simulation report. Once you're finished with the entire project, you can actually then turn this entire report into any kind of a PDF. I'm not sure if my computer will handle this. We'll see. I hope it does. It'll generate automatically a report that you can then work with customers with, or work with agencies with. You can turn it also into a PowerPoint presentation. A lot of different ways that you can use the report to help demonstrate the value of a particular project somewhere. And thinking from a perspective of you know, a government agency in Pakistan, and this is anywhere in the world, if you're looking to get the most impact on the economics of a project, it's really recommended to use a tool like Homer or something like this, just basically a optimization tool that will ensure that your money is being invested in the most wisest way. That's not just going all towards a simple PV only job, when there's other technologies that can really help drive down that cost, or a diesel only cost. What you're looking for is a system that works reliably, but yet delivers the least cost of energy for that particular project. So I'm trying to get to a couple of things here. Here we go. So this is a lot of the outputs that you're going to see is essentially what's going on, the capital costs, the operating costs, replacement costs, and even salvage costs that we take into account. And it really can give you the answers that you're looking for and understand the economics of that particular project. So essentially, that's my presentation. That's kind of an overview of Homer Pro, and I'm certainly open for any questions anybody might have.
Andy, yes, thank you very much. So, do you have some examples to show? Anything else to show, or is it? Are your presentation is finished now?
Yeah, that's finished now. So we went through the last example of the Philippine village. I hope everyone saw everything. I was having some problems with my computer, unfortunately.
No, it was okay. It was fine. We could
Okay,
check
good.
it. Yes. So, okay, Andy, we are going to note down. We are noting down some questions. So, in the meanwhile, if you want to speak something else for 2-3 minutes, you can go on. I'll just grab the questions and then put it up.
Okay, no problem. So I will go back to a presentation. Let's see here. I can get to. One of the things I want to point out is just the different types of technologies that are evolving. You know, for those that are, I'm sure everyone's quite familiar with solar photovoltaics. In solar specifically, comes a lot of different variations. The three most important ones that we see today, and probably the most reliable, are monocrystalline, polycrystalline, and thin film. When you are looking at those designs, it's important that these technologies have some kind of a certification provided to them, usually by an independent laboratory. It has to be like an IEC certification or a UL certification based in the United States, or a CSA if it's in Canada. These are specific types. Some people will say they're CE certified. Well, that really isn't a certification, so it's really important to understand that. Likewise with wind generators. Wind generators of smaller scale, certainly the ones that I've once manufactured many of, they've fallen out of favor for the most part because the cost of solar has gotten so cheap. But there are also some really good wind turbines out there, even in the small scale systems. And some of the biggest advancements in wind technology lately have been in the length of the blade, and so advanced fiber materials for the blades have gotten to the point where you can actually design very effective long blades which are designed to capture more energy in lower winds. Generators and control systems. So generators, of course, have been around for a very long time. We actually work and partner with a lot of generator companies because they also see their world is changing very rapidly because of this emerging distributed energy market. And so they're working with us to work with these other companies to combine their gen sets together. And they use a lot of what we call a microgrid controller, which is looking at this is largely a software technology. There are some hardware is also built into it, but it's largely software, which is there to actually look at these technologies, looks at the load, and it helps make a decision as what's the most cost-effective technology to use at that given moment. Sometimes you have both of them available, and so it's going to pick which one makes the most sense. And probably some of the greatest changes I'm seeing these days is really here in energy storage. You know, just 10 years ago, lead acid was kind of the way to go. It was the both, and it still really has a lot of potential. But we're seeing a lot of changes emerging in the lithium ion world. lithium was originally designed to help make batteries lighter. Everyone probably there in the room has a lithium-ion battery in their cell phone or in their laptop. 10 years ago, your laptops weighed 3 or 4, 1 or 2 more kilos more than they do today because of the lead acid technology. We're also seeing a lot of other areas within batteries changing too. So there's a lot of flow type batteries, which are designed for very large storage systems, as well as I'm trying to think of some of these hot sulfur batteries as well. I was in Dusseldorf a few weeks ago, learning a lot about these more unusual battery technologies, but also have a lot of merit as well. So there's just an immense amount of technologies that are at our fingertips, and a lot of these things are becoming very reliable. But it is really important that specifications need to have certifications on them, need to be, I'm sure you know, that reputable organizations that help build those. Too often these things are built and people forget about them, and the company goes out and the whole project is lost. So I can't stress enough about this is an exciting time, but at the same time, you have to really pay attention to the details.
Thank you very much, Andy. So we have gathered out few couple of questions from our participants. So the first question to us is a bit out of context from the Homer perspective, but you as an expert on the energy projects, how do you see the battery storage role in next 2 to 3 years?
It's a very good question, and we've been predicting so there's two things that are going to happen. One is the technology, and especially so there's two primary markets, right? There's what we call stationary batteries and vehicle transportation batteries. They're not that different overall, the batteries, but the vehicle market is really what's driving the falling prices in storage. What we saw was a race as lithium evolved. We saw a race to build very large factories. It started with Tesla in America building what they call the Gigafactory, but then China, of course, quickly jumped in there with companies like BYD and Foxconn, which is the company that makes the Apple phones, and a number of others that are really creating so much capacity on the market that we could literally see another falling of another war, similar to the way we saw with photovoltaics in the mid 2005 to 2008, where we saw solar panels drop from $3 a watt to less than $1 a watt within about 5 years. So what we see is a continuation of that. We think that they won't see as many real breakthroughs in lithium technology. You'll see a lot of incremental improvements in the technology, which is going to drive greater capacity, energy storage capacity, and probably longer lives to them. But all on top of that, we're going to probably see another, I'd say every year over year, somewhere between 7 to 14% drop in battery prices year over year. So it's quite an exciting time because it only improves the opportunity for microgrids.
Thank you, Andy. Thank you very much. So, Andy, I have a question from you, from myself. I mean, in your software, you have shown that you can limit the amount of emissions from these gases, NOx and SOx. You can limit those emissions. But from the perspective of after the evaluation, if you have different technologies, but your software only gives the analysis based on the economic side. So is there any way that we can check out or compare 2, 3 different options after the simulation on the basis of economics plus the emissions emitted from that option?
So yes, the answer is yes. So you can do that just with even just the sensitivities here. You can create 2 or 3 sensitivities and say, I'm going to compare the what's the impact of reducing the economics. And I can tell you, I'll show you if I can pull it up quickly. Another presentation I did not too long ago, which let's see here if I can just here and get to here. So this is an example of a presentation that I did a while ago, which is looking at what we call the 100% the challenge of 100% renewables. Renewable energy works. It works very well at reducing the cost of a system, but when you get too high of a penetration of renewables in the system, the actual cost of energy will actually go up, and it's more that last 20%. So you can actually run the scenarios that you were just suggesting with a sensitivity analysis, and then you can see then and chart out the impacts of what that would look like in a model. And so what happens if you get above, and we tell people this all the time, when you get above 80% renewables penetration, you're going to see the cost of your system go up very high. And you can get to 100% renewables, but it's going to be very expensive.
Okay, thank you, Andy. So, Andy, one another question is which small scale renewable energy technologies are likely to make a significant impact on energy solutions in the near future?
The biggest one is really going to be solar plus storage is probably going to have the greatest impact in the very near term. And that can be done like in America, for example. There are over 1 million homes now and businesses that have PV systems installed. In the year 2000, there was about 500 systems. So we've seen just in the last 20 years a dramatic change in the number. And I'd probably say majority of those systems were installed from around 2008 till until 2019. So some of the biggest changes is really directly driven by those two technologies.
Solar PV. And another question is very close to this question also. I mean, how do you see an effective role of supercapacitors in energy storage in next 3 to 5 years? We already talked a lot about lithium-ion batteries. So, what is the role of supercapacitors?
So supercapacitors, have the ability to charge very rapidly and then discharge over time. They're not so effective on as a battery. I know that Tesla has been doing a lot of research in that area. They're trying to enhance that. The beautiful thing about it again is that you can charge a supercapacitor extremely very, very quickly. I mean, it's also challenging because if you have too big of a capacitor, you've got to also take into account the where the energy comes from as well. But it's I don't see it taking a very big role at this point in time, largely because just the cost of, again, it goes all back to economics. You can build certain supercapacitors to do certain things, but long term, I just don't see that there's going to be a significant marketplace in terms of them replacing batteries or something like that.
Okay, thank you, Andy. Since your main expertise is in the micro wind turbines, so we also have a similar question related to this technology. The operation and maintenance issues in the villages which are far flung from the main grid, and what are the general problems or issues, and how does the software take care of these issues? Do you have any idea on that?
Yes, so the Homer software does not. Homer software can take account for the cost associated with what we think that the maintenance cost would be, but it doesn't necessarily do anything about that. But within a good microgrid system, you'll have a microgrid controller. And now here's where the challenge gets in, because if you've got a village way in the north and they don't have internet connection, that sometimes can be a challenge. There are other ways of getting the information out of a location using even satellite communications, because it doesn't take a lot. But generally in my experience, in my past, what we did oftentimes, and this is it works and it sometimes doesn't work. It's training the local person or a couple of people within that village and part of their job, and they get paid for it through the utility of through the investment, is to help do the maintenance on that. Now, the challenge that I see is that when people learn about doing things like this, they often want to go to the city because they can make more money. So it's that can be sometimes of a challenge. But a lot of these technologies nowadays are very advanced. They have sensors all over the systems. They're looking at energy consumption. They're looking at battery charge cycles. They can even look at the cell level at the PV array, and then signals back to the main station, if you will, that can say, okay, there's a problem with this. It's not a problem right now, but we predict within 6 months it's going to be a problem, and that someone should go there and replace a part. But there's a lot of really great products and companies out there that are developing these controllers that can do everything from collect revenue from the consumers in these areas to keeping an eye on the operational operations of that facility.
Okay, thank you, Andy. So, Andy, another question is you mentioned a lot about the sensitivity analysis of this Homer software. So, I have a question. You talked about the in the sensitivity analysis, if we can put some numbers, like for example, diesel prices go higher, maybe 30% if they go higher than the current prices in next 5 to 6 years. How does the software? You didn't show that aspect too much. I would like to you to answer that one. Secondly, with the reduced prices of solar PV and wind generators, and if their operation and maintenance costs are also reducing with time, so can we put this into the sensitivity analysis just to make renewables more attractive comparable to the diesel one?
Okay, so Homer calculates that automatically, so you don't have to account for. So we look at the initial investment of the component, and then we depreciate it over time. So there's the initial capital costs, and then throughout the life of its design, we take account for the lowering operating costs. So when it gets to zero, it still has life in there. Then it's reflected in the actual cost of the system. So we do that already. But when it comes to the sensitivities, everywhere through the software, you see these little circles with this little brackets. These are your sensitivity calculations. And so virtually everywhere in the design, you would just click on the item, and so you can plug in these penalties, or for example, in this particular one, or in economics, if we wanted to look at inflation rates, we can say, well, maybe there's a 3% and then 4% or something like that, and we click on OK, and you see it pops up these little 3 here, and that means that it's gonna run that. And then when you go to the results section, which I was having problems with the software, so I'm not sure if I can get to work this for. This up here is all those sensitivity cases that we ran, and so we were looking at all those. So when Homer was finished with running the models, it said that this here happens to be the most cost effective of the sensitivity cases. And then it goes up from there. You can see it from 68,000 in net present cost to 89, 90,000. So and so in each one of these, if I click on the sensitivity case, or if I want to click on this sensitivity case, you'll see it change down here. And so within this sensitivity, it ran all of these optimizations within that sensitivity, and this is the winner of that particular one.
Okay, thank you, Andy. So, Andy, one of the question is from the participant that how accurate are the system variables like temperature, wind velocity, and solar radiation? Plus, another question is that the economics of projects, who determines the economics of project? That is the discount rates, inflation, and project lifetime. The second part, I think you don't need to answer because we as a user feed these information into the software. First, you can answer a bit about how these radiations and temperature are.
Right. So I'm missing the question. So repeat the question again. I'm sorry.
Well, the question is how accurate are the system variables like temperature, wind velocity, and solar radiation? I think he's asking from the
Okay.
perspective of his resource.
Okay. So when it comes to, so on the diesel side, we don't account for a couple things, and this is actually something we're working on in the model specific to diesels. They will have a difference in operating temperature based on the ambient temperature and also elevation. And currently, the only way we can make those adjustments is by manually adjusting those. So we have a kind of a workaround, but we have a new version coming out relatively soon where we will account for elevation variations and also temperature. So when you look at a generator right now, let me go to components and generator. Um, so right now, what we look at is you can adjust a fuel curve based on and change this based on elevation. It's not the right way to do it, I think, and so you'll see that actually change quite soon. But there's a lot of different ways that you could make adjustments here. If you have specific types of maintenance, or if you have a maintenance schedule that you need to set up for the generator to come on at certain times, we can account for that. Um, we can account for then customizing the emissions on it. If it's a biogas generator, we can also do that. We can change the design around. And of course, I mentioned earlier, we can change the fuel types. Here, this here has a very
Yes, yes,
low. I'm sorry.
please go ahead, go ahead. Keep.
Okay, so in here, for example, we have three sensitivities set up for fuel types. So we've set 25 cents, 75, and a $1.25 liter. I wish we could spend. I wish diesel fuel was 25 cents a liter. That would be nice. But so all through here, there's a lot of different functionalities. Lifetime, minimum runtime. We also have capacity. I'm trying to think where it is here. Operational capacity has to be at a certain. Oh, here it is. Minimum load ratio is what that's called. So that you can make sure you protect the generator from wet stacking and whatnot. I hope I answered that correctly.
Yes, okay. Thank you, Andy. It was okay. So, one question from the Afghanistan. There is one delegate from there. He has asked a question that is this software available for Afghanistan? Plus, in the Homer software, how long will the free version work? And is there any training for Afghanistan or SAARC region? I mean, do your company provides any training kind of a thing?
Yes, so we so I missed the first question. It's available how?
Is it available for Afghanistan? Does your software takes care of the Afghanistan data, Afghanistan project?
Um, I believe that, yeah, the answer is yes to that. Well, one thing I do want to demonstrate too is on economics and currency. We can also set the currency. So if you prefer not to figure it out in dollars, you can figure it out in the Pakistani rupee, for example. And
Okay.
so it'll work in any currency as well. So I want to bring that up. There it goes. It took a minute for it to catch in there. But so it'll take it and calculate everything in rupees. The free version is available for 21 days for free. You can play with it. If you need a little bit more time to try it out, just have to write to me directly, and then I can make some adjustments to your trial. Um, but once you purchase the software, it comes with really it's just sort of an introduction. It's a free introduction to Homer. Runs about 3 hours, 2.5 hours. We put on a whole live class, basically using GoToMeeting as well, in the same way that we're doing today. But then we also can do foundation trainings the same way. Those last about 6 hours. Um, and and then when it gets beyond that, it gets more challenging over the web because it takes a long time. But we do oftentimes live trainings all around the world. So if there was like usually we like to see up to 15 people in a classroom we can put on 2-3 day trainings at your location there, or we can find a right location anywhere in the world. We're putting one on Crete in Crete in just a couple weeks. We've put them on in just every corner of the world.
Thank you, Andy. I think you have answered his question. So, Mr. Zafruddin from Afghanistan can talk with his ministry and maybe try to engage you in the future for any kind of trainings. So, Andy, last question. In your experience, which are the main challenges to the use of microgrids in South Asia region or other developing countries? Are these challenges technical or financial?
I would say the biggest challenge is financial. A lot of the technology is working very soundly. We've been designing and building microgrids for many years, and so the equipment working together in harmony, a lot of that has been fully vetted out. The bigger challenge comes down to the financial side, and not so much the financial side from just the condition of the country, but when a financial organization wants to look at the risk, they have to do what's called a risk assessment of the project. And so they look at each component. When it's just a solar system and perhaps some batteries, it's relatively easy to do because it's just two technologies, or maybe three with the inverter. But when you start combining multiple other technologies to the challenges are greater, and trying to understand, well, who pays for, the system goes down if, one technology or another fails within the overall design. So a lot of that's being worked out and discussed, but it's just part of the process of as this world evolves into where it seems to be going. And so the other problem that I've seen in Southeast Asia is sometimes people will under design systems. They maybe won't use a diesel generator. They might just use solar and storage, and it limits the amount of energy that the user can use. And that's not how these things should be designed. They should be designed in such a way that it provides functionality for them. So more than just some lights, for example. Because as soon as people, in my experience in traveling all over Asia and Africa, the biggest challenge that comes out is when people they get electricity in their home, and then they want, all of a sudden, they want a television, and then all of a sudden they want a refrigerator and a couple ceiling fans or something, and so that adds to the load, and that's what cripples the system if they're not designed correctly.
Thank you very much, Andy. Uh, so with this, we don't have any more questions. So with this, I may like to conclude our webinar. Thank you everyone for attending today's session of the webinar. We have listened to an excellent presentation delivered by Andy from Homer Energy Company. The recording of this webinar will be available on SAARC Energy Center's YouTube channel very shortly. We would love to hear from you any suggestions and comments for further improvement, plus any suggested topics of your interest on which you want us to arrange future webinars. We would gladly do that. So we are also thankful, very thankful to Andy and his company for joining us in this webinar and to introducing the webinar with introducing his software with the participants. And with me signing out, thank you again for joining us today. Have a nice day and bye bye.
Okay, thank you. Bye-bye.
Thank you. Bye bye.